Hey there, chemistry students. This is Mr. York. This is podcast 4.2, where we're going to learn significant figures. You guys are going to love this. Okay, in the last podcast, we were talking about uncertainty in measurements and where you have precision and accuracy. Well, measurements in science need to be accurate, and if they have to be accurate, then they also have to be precise, right? Because they need to be close to correct as possible, and they need to be consistent. And if they're not consistent, then your data and your results are bad and you need to start over. So uncertainty in measurements are based upon the significant figures that are used. And you'll also hear significant digits, but significant figures that you use is what makes up tells you how certain you are in your measurements. So significant figures are made up of all digits that are certain and then one additional digit that we represent as an estimation. So all numbers that you know and one that you guess. So for example, if we were reading off of a ruler or an instrument, we would do it this way, where we would read on this. I know it's fuzzy, but this is 0, this is 1 inch, this is 2 inches, 3 inches, 4 inches, and 5 inches. Right? And this line falls in here right about there. And so we know it's between 4 and 5 inches. Well, if we were to make it just a little bit bigger, there's 4, there's 5. This would be 4.1, 4.2, 4.3, 4.4, 4.5. 4.6, we know that the measurement of the pencil would be between 4.7 and 4.8. That we know for sure, that it's between 4.7 and 4.8. We don't know anything else for sure. Now, because it hasn't reached 4.8, we say it is 4.7. We know that for sure. Now, significant figures, when we're reading this, we have to read all numbers that we know for sure, and then one that we make an educated guess on. Okay, so we're going to pick a number that goes in between these two lines here. We're going to pretend like this is blown up even more. And when we blow this up even more, we have graduated lines, that 1 through, 0 through 10, and we guess where we think that the edge of the ruler or the edge of the pencil falls. So you could guess 4.72. You could guess 4.73. You could guess 4.74. They would all be viable. And if you guessed one of those, I couldn't say if you were right or wrong, so I would just say that you're correct. Because it's all numbers that we know and one that we guess. All right. So in this case, the 4 and the 7 are our certain numbers. And then the 2, the 3, or the 4 in the hundredths place is the uncertain or the guessed digit based upon what the ruler reads to. And that would tell us the accuracy, or excuse me, the precision of that ruler. All right, so we use significant figures, and okay, these are the certain or the known numbers in a measurement. Exact numbers are counted and have unlimited significant figures. So an exact number is a counted digit. So we know that in 1 dozen there are 12 eggs in a dozen eggs, right? That would be, it's an exact number. And if you have an exact number, there are unlimited number of significant figures, and we don't use those to calculate anything. So anytime it's a counted thing. If I counted up 26 students, that would be an exact number. Right? If we said that there were 1,900 students if there are exactly 1,940 students in the school, that's an exact number. All right. All non-zero numbers are going to be significant. All right, so what does that mean? Well, that means they all count. They go towards the measurement. And a non-zero would be anything that's 1, 2, 3, 4, 5, 6, 7, 8, or 9. All of those are significant. Okay, and then you have your zeros. Now your zeros are very, very special. We have 3 types of zeros. You have zeros that are leading, which means they're in the front. You have zeros that are trailing, which means they're in the back. And then you have zeros that are in the middle. And I call those sandwich zeros. But we can say they're in the middle. All right, so 3 different types. We have trailing zero, or sorry, not trailing, leading zeros. If a 0 is at the beginning of a number, it doesn't count towards the number. It's not significant. It's simply a place value. It's just holding. It's holding a place. So a leading 0 or zeros at the beginning are never significant. All right, what about the middle zeros, the ones that are sandwich zeros? Those are always significant. And then the trailing zeros, or the ones that are at the end of a number, are only significant if a decimal is physically present in that number. Okay, so what in the world does that mean, Mr. Lark? Well, if I gave you these numbers here and I said, tell me how many of these are significant, you have to use these rules here. So 3 and 2 are both non-zeros. They both count. So that one counts and that one counts. These two zeros are trailing zeros. And remember, trailing zeros are only significant if a decimal is physically present. Now, is a decimal physically present in that number? No. And if it's not, then they don't count. So there would only be two significant figures in that number. All right, on this one, we have a 3, it counts, the 2 counts, 2 trailing zeros, so we say it's only significant if a decimal is physically present. Is that decimal physically present? Yes, so all of the zeros at the end will count, and there are 4 significant figures in that number. All right, what about 0.003? All right, all the zeros at the beginning of a number, leading zeros, are never significant. You said, but wait a minute, there's a decimal present. Yeah, but that's only for ones that come after anything at the end, right? Only the ones at the end. These are still at the beginning of a number. They don't count. So there's only going to be one significant figure in this number. All right, so how many significant figures do the following numbers have? I'll do the odds with you, and you're going to do the evens for practice. All right, so the first one, 1.032. This 0 is in the middle, so it counts. There would be 4 significant figures. 6800, the 6 counts, the 8 counts, but the 2 zeros at the end don't count because there is no decimal physically present, so it would be 2 significant figures. Problem number 5, 2.46. They're all non-zeros, so they all 3 count. They are 3 significant figures. Problem number 7. The 6 counts, the 8 counts, because they're non-zeros. Those 3 zeros at the end only count if a decimal is physically present. Well, look what. It's physically present. And so they all count at the end because they're all trailing and there's a decimal physically present. All right, here we have 0.0010200. Lots of zeros, right? All right, these at the beginning never count. Why? Because they're leading. The 1 counts. Does the 0 here between those 2 count? Yes, because it's a middle or sandwich 0. The 2 counts because it's a non-zero. And these 2 zeros at the end, do they count? Well, because there's a decimal physically present, guess what? They do. So there would be a total of 5 significant figures here. All right, go ahead and try the other ones, the evens, and bring them to class with you and we'll check them. All right, so in this class, we're going to have to use significant figures when we do our calculations. There are a couple rules that you need to follow. They're very simple rules, just don't mix them up. All right, for multiplication and division, your answer has to have the same number of significant figures as the number in the problem with the least number of significant figures. Okay, so for example here we have 1.31 times 2.2. So we would plug this into our calculator, and when we plug that into the calculator gives us 2.882. But according to our significant figure rule, we have to have the same number of significant figures as the one that has the least in the problem. So there are 3 significant figures here. There are 2 significant figures here, so we have to round this number to 2 significant figures. We're always going to start on the left-hand side. The 2 counts, the 8 counts, that's 2. Everything else is going to go away, but before it goes away, we have to see, does the 8 make the 8 change? Yes, it does. It makes it become 2.9. All right, we're going to practice lots, don't worry. Okay, for addition and subtraction, there's a slightly different rule. On this one, you're worried about decimal places. So you're going to have the same number of decimal places in your answer as the one in the problem with the least number of decimal places. All right, so 1.31 plus 2.2, and the answer gives us 3.51. All right, but when we look at it, we have 2 numbers after the decimal here. We have 1 number after the decimal here, and this one's the smallest, so we go with that. So we need to have 1 number after the decimal. Does the 1 make the 5 change? Nope, it's not strong enough. Okay, so here's some for you to try. I want you to do the odds with me, and then the evens you're going to do on your own. So for problem number 1, we have 2.36 plus 1.7 plus 3.284. And when you put that in the calculator tells us 7.344. All right, it's addition and subtraction, so we need decimal places. This one has 2, this one has 1, and this one has 3. This one, 1 is the smallest number, so we're going to round to make sure that we just have 1 number after the decimal. The 4, does it make the 3 change? No, so 7.3. All right, for problem number 3, 8.2 divided by 3.74 gives us a very long number, 2.192513337. It keeps going, but I'm just going to stop. All right, we have division, so we need to know significant figures. This one has 2 significant figures. Oops, that's supposed to be a 2. And this one has 3. 2 or 3, which one's smaller? 2 is smaller, so we have to round this so that there are only 2. The 9 makes the 1 go up, so it should be 2.2. All right, problem number 5, 12.036 minus 3.42 minus 2.067. And the calculator gives us 6.549. All right, how many remember decimal places because it's addition subtraction. Well, there are 3 here, there are 2 here, and there are 3 here. We just need 2. So we keep these 2 numbers after the decimal. The 9 makes the 4 become a 5, 6.55. And then for number 7, we have 13.040 divided by 3.23, and the calculator gives us 4.0371517. It doesn't matter. Okay, significant figures. Remember, significant figures. In this problem here, there are 5. And in this problem here, there are 3. Which one's smaller? 3. So we keep the 4. Is the 0 significant? Yeah, because it's in between 2 non-zeros. And the 3. Does the 7 make the 3 change? Yes, it does. So it should be 4.04. Okay, we'll practice lots of this in class. And I thought this was hilarious. And there you go. So I'll see you in class, guys.